All right, well, welcome back. So you should have finished your exam. Hopefully that went well. Um, I think your TAs are shooting to get those grades back to you within roughly a week. I will post the answers. I want to make sure that if there are any late ones that come in, I want those to come in before I post the answers, obviously. So, but I will be posting them uh, this week as well. So this next section of the course gets a bit more sort of quantitative, um, a bit more mathy, right? Fewer interesting stories about Freud and Newton and stuff. Um, so I think the book does a good job of keeping it really very simple, not a lot of like, it's really primarily like subtraction and addition, and being able to sort of like keep in your head like converting percentages to decimals, right? 75% is 0.75 and so on. So not a ton of math stuff. Um, and in order to keep it this simple, they do simplify a bit some of the actual statistical methods. They always point it out when they do, and in the appendix they give you the proper method. Um, but they give you things that are good enough rules of thumb, right, for us to be able to use them in our daily lives. So um, if you're a super statistics person, hopefully you won't get annoyed at this sort of simplification. And then if you're a person that struggles with this sort of quantitative stuff, I really hope that it's gonna, I'm gonna try to take it slow and make sure that we don't fall behind and do just sort of like try to stick it out and do the exercises, ask questions and discussion, right? Is a place where I hope we don't lose people, right? Um, so I think, in fact, to that end, I think I'm going to have to change the syllabus a bit, and I'm going to make chap. So this week is chapter 5, right? And it's in two parts. And then I was going to do chapter 6 just in one lecture, but having sort of like to put together the lectures, I'm realizing that would be too much, too fast. So I'm splitting chapter 6 up into two lectures as well, which may mean we have to drop chapter 10 at the end. So I'll make the modifications on the syllabus, but I really want to take this at a reasonable pace, right? So that we don't lose anyone. All right, so well, then let's get to it. So statistical and probabilistic models, right? So in many types of science, many of the ones that are actually sort of most directly relevant to your life, these are social, behavioral, biomedical sciences. Um, they often make use of these probabilistic models. Um, so, I mean, the point of this course is for you to be able to read scientific episodes and popular literature and figure out, right, evaluate those episodes and decide if and how you need to apply that information to your life. So a lot of the sort of most relevant stuff is of this nature. So you might want to know, okay, what percentage of people have COVID right now? I kind of do this on a daily basis. I wake up in the morning, I look at the numbers in the LA Times, and I see, okay, I do a little calculation. I see, okay, looks like I mean, lately it's been like 1 in 10 people, I think, has it, right? If you sort of take their numbers and then do a rule of thumb or multiply it by 4 for people that aren't getting tested, which is what I've seen. So, anyways, other times it's been much, much lower, right? Less than 1 in 100, 1 in 500, or something like that. So, you know, that's good information to know. If you're walking into a room with 10 people, ooh, maybe one of them has COVID. Um, what percentage of American women ages 20 to 30 hold full-time? What percentage of applicants to whatever sort of graduate program you're trying to get into are admitted, right? That gives you roughly, a sense of the probability of your being admitted. So this kind of stuff is definitely useful in your life. So it's good to have a basic grounding in what this stuff means. And I think this text does a good job of doing that in a way that I think all of us can follow. So what would we do if we wanted to answer that question? What would we do if we wanted to know what percentage of American women ages 20 to 30 hold full-time jobs? Well, if you could find every woman in the US, you could just ask them and add it up, right? Um, that's incredibly impractical and likely even impossible, right, to chase down every single um, person in a certain group. So the way we typically accomplish, right, find out this information is we just take a sample of the whole population, right, and then use that sample, right, the information we gain from that as evidence for a hypothesis about the population, right? So in order to formulate those sorts of hypotheses and evaluate them, we need probabilistic models. Another thing, right, another reason you might need these statistical and probabilistic models um, is that often we want to know about causation, right, as regards some characteristic of interest in the population, right? So we might want to know do does eating foods high in cholesterol cause heart attacks in men, right? Um, we want to we certainly often want to know causal questions like these, right? What are in pregnancy, right? What are sort of causes of bad health outcomes for the child, or what are causes of good health outcomes, and so on. But often, first of all, we may not have enough sort of understanding of the actual biological mechanisms, right, that are going on in order to answer that question for any particular person. And often it would be unethical to perform the sort of experiment that you might need to do in order to figure out those mechanisms, right? So you can't just take a group of men and feed them cholesterol until they have heart attacks, right? And um, same with right all the information we know about pregnancy and right childbirth and stuff like that. I mean, you can't just do experiments on pregnant women and see what causes bad outcomes and what causes good outcomes. So um, these statistical methods can give us information, and even in these cases where it's difficult to assess it directly, right? If you study again with the question of men and cholesterol and heart attacks, you study several large groups of men. Often we can find good answers to these causal questions, even if we don't quite understand the precise mechanisms of how that causal relationship works. Um, but in order to do this, also we need probabilistic models. Okay, so let's start from scratch, right? What are the basic elements of a statistical study, right? If we want to look at a population, we want to know something about that population, and we're going to do that by taking a sample, right? Um, what are the parts? Well, this is some terminology we need, right? So um, sort of the real world part, you're used to the real world part of a model, right? Well, here, the real world part is the population that is the object of interest. So in the example here, American women ages 20 to 30. It can be that specific. It doesn't need to be the whole US, the whole world, or anything like that. They don't even have to be actual people, right? So often, like when the US Census, um, their sort of unit of the population is households, right? So it's a population of households. Um, if the FBI is studying homicides, right, these are events, right? And you can have a population that's made up of all these events, every homicide, right, in the US in a certain year or whatever. So in our examples, working through all these details, we're going to be using a population of marbles for a lot of it. Right? So it doesn't have to be people, even though we use the word population. Um, so whatever sort of thing, right, comprises your population, um, we're going to be interested in certain properties, right, that the individuals in that population have, right? We want to know how many of these individuals in the population have a particular property, right? If the population is, again, American women 20 to 30, we want to know how many of them have the property of having a job. Um, they can include anything, right? Having a full-time job. If we're looking at crimes, right, as our population, they might be which crimes are involve a gun, right? That's a property involving a gun, and so on, right? We'll be looking at marbles and their colors and their size. Those colors and the size are the properties of interest, right? So the properties, if we're talking about the model, we want to know what's the real world. The population of interest is the real world, but also the properties that we're interested in, whether what proportions are in the population, those are also part of the real world, right? And as we've said, since most populations are too big to examine exhaustively one by one, the best we can typically do is examine selected members of that population, and we call that a sample, right? We'll get much more into detail on how the sample is selected and what's the right and wrong ways to select a sample. But for now, keep in mind the sample is also part of the real world too. It's part of that actual population. It's just a subset. Um, Selecting the sample, it's a physical process in the real world carried out by real people in the real world. So it's not part of the model. Okay, so that was sort of the left-hand side of we'll see our little chart of like the statistical model and, or sorry, sort of a statistical scientific, I guess. Um, so there's the real world part that includes the population and the sample, and then we've got the model part. Um, you need a model of the real world population in order to do a statistical study. So there's going to be a statistical model. It could be something very abstract, like a set of numbers, right? Or it could be a real sort of jar of marbles that sort of models right, the real world population. But whatever you use as the model, um, it's going to be distinct from the real world population. It's standing. Um, so you've got the real world, you've got your real world sample, you've got your model of the real world population. You're also going to have a model of the sample. And the model of the sample is going to be drawn from the model of, right? So the picture looks something like this. Again, as I said on the left, we've got the real world population from which we draw a real world sample. And then we've got a model of the population from which we draw a model of the sample. And the question is there fit? Is there good fit, right, between the model and the real world? So we can see sort of broadly how the elements of the statistical study are similar to the elements of the theoretical hypothesis that we've been covering so far. Again, we got the real world on the left side, population, the sample drawn from it. On the right side, we've got the model and the model of the real world sample that's derived from the model. So the process on the left side in the real world is like a physical process of like, right, examining actual people in the real world, asking them questions, giving them surveys, right, whatever your process is of taking the sample. Um, in the model side, it's going to be a process of inference from the model. Now so those are the similarities, right, between what we've seen so far, our models so far, scientific episodes of evaluation. The difference here is that instead of using data from an experiment, right, there's not going to be an interaction with the real world in the fit. We're going to use some other auxiliary information and some calculations to determine that fit. So for the rest of this lecture, right, we're just going to be focusing on the right side, right, developing what it is to have a model of a population, what it is to have a model of a sample, and the relations between them. Okay, let's take a moment for you to take the quiz. Here's the link. That should be enough time, I hope, for you to copy that link over. And if not, of course, just pause the video. So we will move on. So let's use a jar of marbles as our model for a population, right? So each marble is going to have certain properties. Different marbles can have different properties. Um, it's just a bit simpler, right, than a human or other sort of real world populations. And we'll even sort of keep it pretty simple. With the marbles, we'll stick to things like color and size, right? Um, One thing we can model with our jar of marbles is the proportion of marbles that have some property. So similar, right, to our question about, what proportion of women in America age 20 to 30 have a full-time job, right? In principle, no different a type of question to ask, okay, what proportion of marbles in the jar are red, right? Um, so if there are 100 marbles in the jar, 60 of them are red, then the proportion of marbles is 60 out of 100. You could also rewrite that as 6 out of 10, You could write it as 0.6. You could write it as 60%. Um, those are all equivalent. And you will find that in the rest of these lectures and in the book, they're going to assume that you're fairly comfortable moving back and forth between those versions, percentages to decimals and so on. So if you're a little rusty on that, it takes some time to review it, sort of get used to that. You're gonna need that. Again, it doesn't get super mathy, but some certain basic sort of arithmetic is going to be unavoidable, right? So here is a little diagram of our model, our jar of marbles, and there's 100 in there, right? So we see that 60% are red, and we can infer that 40% are non-red. So let's pause real quickly and introduce some more terminology. Um, when I introduce a term, right, it's on purpose, and you're going to need it. So pay attention to these, because in order to be precise, um, that's why these are introduced, so that the language can be precise and regimented. And so after it's introduced, it's going to be used a lot, right? So that when the authors and when I say something uh, to describe these processes of inference, right, that we're going to use this terminology so that our language can be precise. So do pay attention and try to keep up and go back. If you hear a term you don't you're not sure what it means, don't just try to just gloss over it and keep going. Pause, right? Go back, make sure you know what's being talked about. You have to move a bit slowly for this. So here's some of our new terminology. Variable, right? So a variable is a property, very general property that can have different specific forms. So example, color is a variable, right? It can have specific forms like red, green, blue, etc. Um, size is a variable, right? Whose specific forms could be small, large, etc. So the specific forms have a name. Those are called the values of the variable. So we'll be using those terms a lot. So color is a variable, and it's got possible values, right, that will be specified. They might be red, green. So let's take our jar of marbles, right? Let's say that the variable color has 3 values, right? It's our jar, right? We can decide how many values we want to have in there. So we've just stipulated that there's only 3, red, green, and blue. So one thing we need for this sort of enterprise to work, right, to have a model that's going to be able to give us conclusions about with a real world sample or real world population, is that the set of possible values involved for a variable need to be exclusive and exhaustive, right? Um, so what do those mean? Well, for a value of a variable to be exclusive means that a member of the population can only exhibit one value, right? So when we say that the values, right, of the variable color are red, green, and blue, that means that marble can't be both red and green. For a value of a variable to be exhaustive, right, that means that every member of the population must exhibit at least one of the specified variables. So, right, if we've specified that our values are red, green, and blue, then none of the marbles are going to be yellow, right? So once you've got, right, once you know all the red marbles, all the green marbles, and the blue marbles, you know about all the marbles, right? There's no other extra marbles hanging out, and every marble is either red, green, or blue, right? It's not like both or neither or anything like that. Okay, this is a bit of an idealization, of course, right? In the real world, right, you might get a marble and you're not sure whether it's blue or purple. How do I classify it? We are eliminating all of that ambiguity. It's going to be very clear at every point, right, how to classify a marble. All right, more terminology. So a distribution. So a statistical distribution is defined with respect to some particular variable with some number of possible values. What that means is for each possible value, right, there's going to be some percentage of the population assigned to that value. So, for example, our jar of 100 marbles, we got 50 reds, 30 greens, 20 blues. The corresponding percentages, because it's 100, right, the percentages are pretty straightforward. 50% red, 30% green, 20% blue. Because the values of the variable are exclusive and exhaustive, they are going to add up to 100, right? You're not counting any marbles twice, and every marble gets counted. So that's our distribution then, right? 50, 30, 20. Right? A proportion is sort of a special case of a distribution where a variable only has two possible values, right? So if you wanted to carve up, I said previous example, but I don't know if I gave this example earlier, but anyways, we could carve up our jar of marbles into red and non-red, right? So there's only two values of the variable, in which case you would be talking about the proportion of red, right, in the jar, as opposed to a distribution of more than two values. So here is, again, our jar, and we have 50% red marbles, 30% green marbles, 20% blue marbles. If you wanted to, you could draw it in a pie chart instead. I think typically we will be sticking to the version on the left. So that is our distribution, right? All right, more terminology, correlations, right? So a correlation is a relationship between two variables, and each of those, right, has various possible values. So let's suppose that our marbles have two variables, color, size. Each of those variables has two possible values, red and green for color, large and small for size. Right? So hopefully fairly simple, straightforward so far. So let's start with cases of where there's no correlation, right? What does it mean for there not to be a correlation between variables? Well, suppose that our jar of marbles, right, our model population, has 60 red and 40 green marbles, right? Okay. Now let's suppose that among the red, we've got 45 large, 15 small. And among the green, so there's fewer greens, right, but we've got 30 large and 10 small. So that means that 75% of the red marbles are large. And even though there's fewer greens, it's still 75% of the green marbles are large, right? If you need to convince yourself of that, you can right, do a little bit of math, divide 45 by 60 and divide 30 by 40, right? Um, since in either case the percentage of large is the same, right, for each value of color, we can say that the variables color and size are not correlated. So, in other words, right, if you're looking for a large marble, there's no advantage in picking any color over another, right? You got the same chance of finding a large whether you pick from the greens or from the reds. So what does it mean for variables to be correlated? Well, if the percentage of large marbles among the red differs at all from the percentage of large marbles among the green, then the two variables of color and size are correlated, right? So to be correlated just means to be not exactly the same, right, percentage. You need slightly different percentage, you mean you've got some sort of correlation. So if the percentage of large marbles among the red is greater than the percentage of large marbles among the green, then being large is positively correlated with being red. So suppose that 45 of the 60 red marbles are large, but only 10 of the 40 green marbles are large. Now you can't go with the raw numbers, right? Because again, it's going to be a percentage, right? So and more red marbles than there are green marbles. But nonetheless, if you run those numbers, 45 divided by 60 is going to be 0.75 or 75%. So 75% of the red marbles are large, but 10 divided by 40, you get only 25% green marbles being large. So in this population, it seems like the properties of red and large tend to go together, right? So a positive correlation just means that the two properties sort of go together. It's just um, red marbles tend to be large more frequently than green marbles. Right? In other words, if you're looking for a large marble, right, you're better off looking among the reds. You'll find one faster among the reds in prob in all probability. If instead there were a smaller percentage of large marbles among the red than among the green, then we would say that being large is negatively correlated with being red. So again, let's suppose that only 15 of the 60 red marbles were large, but that 20 of the 40 green marbles were large. So that would mean, doing a little math, right? 15 divided by 60, 25% of the red marbles are large, and 20 divided by 40, 50% of the green marbles are large. So in this case, we would say being large is negatively correlated with being red. In other words, the two properties don't tend to go. In other words, if you're looking for a large marble, you're better off if you don't look among the reds. You got a better shot looking among the greens. Notice that the correlation doesn't depend on any of these percentages being greater than 50%, right? There just has to be some difference in the percentages. That's all it takes to get a correlation. Now, you may have sort of already noticed that the same correlation can be described in a number of different ways. So, a positive correlation between large and red could also be described as a negative correlation between large and green. Or it could be described as a positive correlation between small and green and a negative correlation between small and red. That should make sense, I should think, right? And another thing to point out, correlations, right? The whole sense of having correlation only makes sense with respect to some population, right? So when you're asking if a correlation holds, you're asking if it holds within a population. So it doesn't make sense to talk sort of in general about whether there's a correlation between largeness and redness just properties, right? Uh, you only ask among some group of things, right? Are the large ones and the red ones tend to go together. So another interesting thing about correlations is they're symmetric, right? So look at the two sets of diagrams on the right. So that the top picture describes the no correlation situation in two different ways, and the bottom two charts show the correlation situation in two different ways. My head's on top of one of them, but they're in your book as well. They'll be in the slides. So notice, right, it doesn't matter if you put color on top or size on top. Um, on the top one here, either way you get no correlation, right? So we had been looking at red and seeing what proportion of them were large, but if instead you started with the large marbles and decided and figured what proportion of them are red, you would get 45 out of 75 or 60%. So a different percentage, right? Um, Likewise, if you looked at all the smalls and saw what proportion of them were red, you get 60%. But in either case, you get no correlation, right? Are the same. And then likewise, if you looked at the situation where there is a correlation, um, instead of color on top, you can put size on top, and you'll get different percentages, but you'll nonetheless, right, the percentage will be greater. You will the same correlation will hold. Um, right. So correlations are symmetrical. So those of you who have a little sort of any training in this or heard of correlation may have felt a little puzzled when I said any difference in percentages is a correlation, right? Because maybe instinctively you were thinking that there's a difference between like strong and weak correlation, right? So if I said 51% of the red marbles were large and 49% of the green marbles were large, you might not think that that's much of a correlation, and you'd be right. It would be a weak correlation, right? So strength of a correlation is another concept, right? That we're going to need to get used to. So um, this is what I just said, right? Intuitively, right? If 61% of the red marbles are large and 58% of the green marbles are large, um, I guess you'd have a small advantage if you're looking for a large marble. Sure, go for the reds, but it, you probably won't get a large much faster than if you just looked in the greens. Whereas if 75% of the reds are large and 25% of the greens are large, definitely hit up the reds if you're looking for a large marble, right? And you care about finding it faster. Um, so for our purposes, we are going to sort of learn how to measure the strength of a correlation. We're going to do it in a fairly simple way, but one that's good enough for our purpose, right? So we're just going to take the difference between the two proportions written as decimals, and that's going to be our rough measure of the strength of a correlation. So definition for us, strengths of correlations. The strength of the correlation between the properties of being large and being red in the population, the difference expressed as a decimal between the proportion of large marbles that are red and the proportion of large marbles that are green. So that means if 75% of the reds are large and 25% of the greens are large, then the strength of the correlation between large and red is 0.75 minus 0.25, 0.5. So this is a pretty strong correlation. Just to get a sense of the range, right? The strongest possible correlation would be 1.0. That happens if all the reds are large and none of the greens are large. The smallest possible correlation is negative 1.0, right? That means that none of the reds are large and all of the greens are large. And if there's no correlation at all, then you call strength of the correlation 0. We'll get more into this. We'll see more examples, and we'll be calculating strengths of correlations with the preview, right? And hopefully, if you were worried about the mathiness of this, that's it, right? You're subtracting. Fairly simple. The math is not going to get any harder than what you've just seen, to be honest. The advantage of that is it's very simple, right? It is not the calculation you'd see in a textbook on the subject. So in the appendix of Chapter 5, they do give you the proper way to calculate the correlation coefficient if you're interested in that. But for our purposes in this course, and I think for your purposes in right, if you don't go on to be a psych major or some other science major where you need to know the statistics, you can get by pretty well, right, evaluating scientific episodes that you find in the popular media with this basic method, right? Certainly, if you want to learn more, take a statistics course. So that is the last slide for now. It's a little short, right? But rather than try to jam a whole chapter into one and make it a little bit too long and move a little too fast, I really want to be careful not to lose people when we get into this quantitative stuff. It's a little drier, fewer like colorful explanations and stuff. So I encourage you, with the extra time left over, review the slides, right? Make sure that you understood everything. I want you to have a little extra time to do that rather than just hear me yammer on. So we will stop here at 33 minutes or so. And yeah, make sure you, again, yeah, look at the book, make sure that you're following stuff. Please don't fall behind. Ask questions in discussion. All right, I will see you on Wednesday.